In this tutorial, we are going to have a look at suvat, or applying suvat to kinematics, or motion as it's called in the book for IB. The motion formulae are in subtopic 2.1, and the suvat is just a mnemonic to help you remember the variables, that's all. So it's motion and kinematics depending on where you are. So let's move on to actually looking at the rules and the application of the ideal situation to a problem you might get in a typical IB exam. So the graph above is trying to show the path of a projectile, such as a cannonball being shot from a cannon. Now the cannonball is shot at different angles. Let's have a look at that. So this would be, I think, 75 degrees, this would be 60 degrees, this would be 45 degrees, and this would be 30 degrees. And you can see they've all got different ranges and different paths depending on the angle they are fired at. But these curves are based on ideal suvat. So, and we're going to look at what that means in this tutorial. So the first thing to observe about these curves is that it's symmetrical. It peaks halfway across its range. And this obviously, for this to be true, there has to be zero air friction, and we're going to look at that in a minute. So the first ideal statement is that it has, the projectile cannonball has zero wind resistance or zero friction. Now what this means to you is that you could actually replace range with time and it would look the same shape. So let's call that time, because it makes the next argument a little bit easier to understand. Okay, so there's zero friction, but we still have G. Let's put G in. 2, 3 significant figures. Right, okay, so G is 9.81. Sometimes you can round to 10, but let's keep it at 9.81. The next rule is that when you're doing kinematics and when you're applying suvat, the horizontal movement is constant speed or velocity. The vertical motion has acceleration of g, of gravity, okay? So we have got of g, which is obviously constant. So it's not a changing acceleration. It can't have impulse, it can't hit things, it can't get sudden rocket thrusts turning on midway. It's just something moving through the air with gravity pulling it downwards. Okay, so this is how we get these curves and these paths. Now I've called this time. We can now talk about height versus time. The maximum height occurs at zero velocity. Now that sounds odd, maybe to you. If it sounds odd to you, think about a ball being thrown up in the air. What happens before it starts to come down? So I've drawn a straight line there. That's the zero velocity point. The reason this is so important is because this allows us to make assumptions in the calculations and allows us to get answers from the limited information given to us by the question. Now, if you want to get calculus-y on this, you could, if you were to differentiate this point here, you would get a derivative version of that would be 0. Or if you look at the gradient, if you look at height versus time, that's why I put time in there, the gradient will be the velocity. So you can see the zero gradient is the zero velocity. And that is the midway point, just to put those ticks in there, of the curve. So if you know the time to the maximum height, you know the overall time the ball was in the air, and you know the range as well. So it's fairly easy to get your head around that. So from that, you can imagine the horizontal velocity. Imagine something in space and just being pushed at constant speed. It just keeps moving without anything to stop it. That's what would happen if there wasn't a gravity acceleration pulling the object down as it was going through the air. It would just keep going in this ideal scenario. So that's the way you've got to look at it. You don't have to worry about acceleration for the horizontal component of velocity.